So yesterday we stopped at the point where we discussed what is the matrix that induces a rotation for the j is equal to 1/2 case. So today my goal is to first talk a little bit more about these matrices for spin half. And then we will try to put it in a bigger picture of what we are trying to do. What is it that we are trying to achieve when we solve this angular momentum eigenvalue problem? Okay. So first, let us do some calculations that will help understand the structure of these matrices and so on and so forth. And this might also be useful in solving problems that are quite common in the case of spin half issues. So let us actually try to understand the structure of these matrices. So what is this u of theta that we have written there? So again, this u of theta that I have written there should properly be written as u of theta vector, which is u of theta times n cap, right? So what is it that we are doing here? So we are trying to understand what is the specific operator that induces a rotation in the Hilbert space for j is equal to 1/2. Okay. So more properly, some people also use the symbol D for these matrices and not U. And I will explain the difference between U and D as we go along today. But let us actually look at this matrix. So what is Ni? Ni is some unit vector in this basis. And how many Ni's are possible? Well, there is 3 Ni's corresponding to the 3 Pauli matrices, right? So how should I characterize these Ni's? One easy way I can characterize these Ni's based on what you already know is I can simply call them N1, N2, and N3 to specify the 3 directions of rotation. Okay. Now, please don't confuse this with the dimensionality of the Hilbert space. The dimensionality of the Hilbert space is only 2. Okay. But this is each Ni corresponds to a particular sigma I, sigma 1, sigma 2, or sigma 3. And one convenient way of parameterization is what you do for the usual XYZ space. But this is not the XYZ space. But I can conveniently parameterize this using the usual spherical polar coordinates that you use as sine theta, I think it was cosine phi. This is sine theta, sine phi. And this is cosine theta. Okay. So this is something that many people use. Again, this is not set in stone, but this is usually useful to characterize it this way. So Ni6. So let us actually work out the structure of this matrix, and then I'll make a few remarks about Pauli matrices in general as a continuation of your tutorial sheet last week. So if I use this particular parameterization, what is Ni sigma I? This is basically N1 sigma 1 plus N2 sigma 2 plus N3 sigma 3. Okay, sorry. So this I can write, since I know what sigma 1, sigma 2, sigma 3 are, this matrix can be written as 0 sine theta cosine phi, sine theta cosine phi 0. This is N1 times sigma 1 plus N2 times sigma 2 is 0 minus I sine theta sine phi plus I sine theta sine phi 0. This is my sigma 2. And sigma 3 is 1, 0, 0, 1. So this is cosine theta 0, 0 minus cosine theta. So this matrix Ni sigma I with this parameterization can be written in a nice form. This is equal to, what is this? Cosine theta. And then the 1, 2 entries, sine theta cosine phi minus I sine theta sine phi, which I can write as sine theta e to the minus I phi. Here I can write this as sine theta e to the plus I phi, and this is minus cosine theta. Okay, which means this rotation equals, okay, so you can simply put everything together and do it out. That is not a big deal. But this form of the matrix is something we will explore further in a tutorial problem. I will ask you to work out the eigenvectors of this matrix, and you can always write down a general state in this two-dimensional space as a linear combination of the eigenvectors of this particular matrix, and we will explore in the tutorial problem why this is useful. Okay. So anyway, so if you look at matrices like this is one way in which you can conveniently understand them. So that is the simple point that I'm trying to make here. So the other thing is about the Pauli matrices themselves. So remember that in the tutorial sheet, you figured out that any 2 by 2 matrix can be written as a linear combination of, any 2 by 2 matrix can be written as a linear combination of the 4 matrices, identity, and the 3 sigma i's. Okay. It also turns out that any traceless 2 by 2 matrix can be written as a linear combination of the Pauli matrices. Because the Pauli matrices are all traceless, and since they actually form a basis for all matrices. Suppose if I have a vector space in which my vectors are actually matrices, then I can expand any vector in this space as a linear combination of the basis vectors, and I can use Pauli matrices as a basis vectors in this particular Hilbert space. Okay. So Pauli matrices serve a very useful purpose. Not only are they operators for the j is equal to 1/2 case, they can also be used in the language of linear vector space as basis vectors to expand any 2 by 2 matrix. If you have a general 2 by 2 matrix, you should be able to expand this as a linear combination of the identity matrix and the sigma i's. But if you have a traceless 2 by 2 matrix, it can be written purely as a linear combination of the sigma i's. So what I'm trying to say is that if you have a matrix M, which is in general with non-zero trace, I can write this as some C0 times I plus Ci sigma I. Okay. Now a homework for you is to figure out the expansion coefficients. Okay, so figure out what is C0 and Ci. Try to take, so for example, if I take the trace on both sides, trace M would be C0 times a trace of identity plus Ci trace of sigma I. Trace of sigma I is 0. So C0 is related to the trace of M. It will be 1/2 trace of M, and so on and so forth. So you should be able to figure out what is C0 and Ci given a general matrix M. So you should be able to figure out what, if I write M as some A, B, C, D, then what is the particular decomposition that we are looking at. So what is C? So I should be able to write this as C0 times 1001 plus C1 times 0110 plus C2 times 0 minus II0 plus C3 times 100 minus 1. So in other words, I'm asking you to figure out what is C0, C1, C2, and C3. So which you can figure out in a general fashion using the properties of the Pauli matrices that you discovered in the first tutorial. Okay. So we will explore this further in a tutorial problem if you have any difficulties. So this is the second point that I wanted to make. Now we will get back to the Pauli matrices, and we'll finish the discussion by talking about something that we started talking about in the first semester of quantum mechanics in the context of Stern-Gerlach experiments. Okay. Okay. So let us take a step back. So sigma. So we have written all the Pauli matrices in the basis 1/2 minus 1/2 and 1/2 plus 1/2. Okay. Now, depending on which book you look at, people use, if a spin half is treated in almost every book because this is a very important system. And depending on which book you look at, there is many shorthands because people don't want to write 1/2 minus 1/2, 1/2 plus 1/2 every single time. So some books, so notation wise, some books, for example, Sakurai does this also. He, excuse me. So the minus 1/2 state he calls minus ket, and the plus 1/2 state he calls plus ket. Okay. But some people also look at this as a spin down system and a spin up system. In general, I don't like the last notation, but I might use the plus minus notation in my course because it's easier to deal with. But please notice that that is just a notation. So whenever I write a plus ket in the context of spin 1/2, it simply means the ket with j equals 1/2 and m equals 1/2. Okay. So let us actually figure out what are the eigenvalues and eigenvectors of the other Pauli matrices. So I know that for sigma 3, I know that the two eigenvectors are plus and minus. Okay. I can also expand them if we want to write them in column vectors. The third representation would be, this would be 1, 0, and this would be 0, 1. Okay, they are all equal, and you can use whichever notation you want depending on what problems you are solving. So this corresponds to m equals plus half, and this corresponds to m equals minus, right? But what about, let us say, sigma 1 or sigma 2? Right? Let us look at sigma 1. Sigma 1, now you know that all the Pauli matrices have eigenvalues plus minus 1, right? You have discovered this in your first tutorial. So sigma 1 is 1, 0, 1, 1, 0, okay? If you don't remember the tutorial problem, or if you have disbelieve the result, let us quickly figure out what the eigenvalues are. The eigenvalues are solved by the characteristic equation, sigma 1 minus lambda I equal to 0. So sigma 1 minus lambda I is basically minus lambda 1, 1 minus lambda equals 0. So this tells you that the eigenvalues are lambda square minus 1 equal to 0, which means lambda equals plus minus 1. Right? So that is simple enough. Okay. So let us figure out the eigenvectors of sigma 1. Now remember that sigma 1 is written in the basis of sigma 3. So the structure of the matrix, so the matrix elements of any matrix depend on which basis we are using. So this is something I've repeatedly emphasized throughout this course and the first semester's course also. So we are writing sigma 1 in the basis of sigma 3. That is totally fine. We have to choose some basis, and we have chosen the simultaneous eigenbasis of j square and j3. Okay. So what is the eigenvector that corresponds to, let us say, lambda equal to plus 1? So this follows the eigenvalue equation 0, 1, 1, 0. Let us call this eigenvector some x1, x2 equals plus 1, x1, x2, right? Which tells me from this equation that x1 has to be equal to x2. So the eigenvector that corresponds to the eigenvalue lambda 1 then is x1 is basically 1 over root 2 times 1, 1 in the column vector notation. Or in the plus minus notation, I can also write this as 1 over root 2 times plus plus minus. Okay. Now we can figure out what the other eigenvector is, but you can simply use the fact that they have to be orthogonal to each other. And the lambda equal to minus 1 corresponds to an eigenvector S2, which is an orthogonal combination of this. Right? That has to be equal to 1 minus 1, or equivalently 1 over root 2 times plus minus minus. Okay. So the eigenvector of sigma 1 corresponds to the linear combinations of the eigenvectors of sigma 3 as a symmetric combination and an antisymmetric combination. Okay. So let us revisit the fact that the 3 sigma matrices do not commute means that I cannot measure any one value of sigma simultaneously accurately, right? So let us devise a Stern-Gerlach experiment that actually drives home this point. So what is a Stern-Gerlach experiment? So again, I have some kind of apparatus, right? So some kind of apparatus, okay, that generates some beams. And so let us say that there is some beams that are generated, right? And I measure, so I put a device that measures S, not S. So yeah, so I put some device that measures, let us say sigma 3. Okay, then what are the possible values of measurement? Well, quantum mechanics tells you that the possible values of measurement of sigma 3 are the eigenvalues of sigma 3. So I will get either a beam with eigenvalue equal to plus 1/2 or a beam with eigenvalue equal to minus 1/2, right? In fact, I will get two beams with equal intensities. One has eigenvalue plus 1/2 and one has eigenvalue of sigma 3 equal to minus 1/2. These are the only two possible results of the sigma 3 measurement on a general sample, because those are the only two eigenvalues of sigma 3, and quantum mechanics tells you that the only possible results of measurement are the eigenvalues of the operator that is being measured. Now let us do the same trick that we usually do in this type of experiments, thought experiments. Let us block this beam. Okay, if I block this beam, and then in the path of this beam, if I put another apparatus that measures the same sigma 3, I'm guaranteed to measure only plus 1/2. Why? Because the beam that I'm measuring sigma 3 on is actually an eigenstate of sigma 3 with a particular eigenvalue. So a subsequent measurement of sigma 3 does not change the value of sigma 3. Okay, so this again should be pretty straightforward to you, but I'm still emphasizing it for clarity's sake. But on this plus 1/2 beam, if I now measure, I put an apparatus that measures sigma 1, what will I get? Since sigma 1 and sigma 3 do not commute, which means that the beam that is in an eigenstate of sigma 3 with eigenvalue plus 1/2, that can be written as a linear combination of the sigma 1s. How can I write it down? So how will I figure out what are the possible values for sigma 1 here? Well, the possible values for sigma 1 here are plus 1 and minus 1, or plus 1/2 and minus 1/2 for the sigma 1 also, because okay, I should not say plus 1/2 minus 1/2. It is plus 1 and minus 1, right? I am measuring not sigma 3 but J3, but I'm assuming that you know the difference between those two. It is just a factor of 1/2. So what is the amount of beam that comes out with sigma 1 value plus 1/2, and what is the amount of beam that comes out at the sigma 1 value minus 1/2? I will figure that out by calculating the overlap of the eigenvector of the sigma 3 corresponding to plus 1/2 with either one of the eigenvectors of sigma 1, which means the probability of measuring sigma 1 equals plus 1/2 is, oh sorry, so this is not showing up, so I will reshare this. This is a little bothersome, but that's how it is. Okay, so the probability of measuring sigma 1 equals plus 1/2, I should first find the overlap of sigma 1 equals plus 1/2 state with the eigenvector of sigma 3, which is plus 1/2 in this case, right? This is the overlap of the final with the initial, and I should just square this. Okay, but I know what this is because the eigenvector of sigma 1 equals 1/2 is basically this guy that I've written down this way is basically 1 over root 2 times plus minus, right? So the overlap of this with the plus state is basically 1 over root 2. So the probability of measuring sigma 1 equals 1/2 in this case is just basically half. And the probability of measuring sigma 1 equals minus 1/2 should also be half, because the total probability has to be 1. Okay, so if I put up device that measures sigma 1 in the path of this beam, then I will split this beam again into two, one which has sigma 1 equals 1/2 and one which has sigma 1 equals minus 1/2 with equal intensities. Okay, so this is again the Stern-Gerlach experiment revisited in the context of spin. And now we understand why is it that these guys get split up, because the sigma matrices do not commute. Okay, so the reason I pointed this out is because it makes a connection with what you know already about the basics of quantum mechanics, and you should never forget that. So that is the second point that I wanted to emphasize. Now remember that since the fundamental commutation relations between the J's. So let us switch slightly to something else. So this is, so you can view this as an aside. So remember that when we try to solve this eigenvalue equation for J square and J3, we appeal to the fundamental commutation relations of J square and J3. Right? In principle, we had J square commutes with any component of Ji, but the Ji's do not commute with themselves. Right? So this is the only thing that we used. So the question I think that was also asked before this lecture began is, what is it that we have achieved, right? So let us actually try to put this in context. What is it that we have solved and what is it that we are going to do? So remember, okay. So remember that rotation, the physical rotation is actually a very simple thing to understand, right? So this is something you're actually very used to. In X, Y, Z space, the physical rotation is something very simple to understand. So you know that the rotation in physical space, there is only three matrices possible, right? A rotation around the x-axis, a rotation around the y-axis, and a rotation around the z-axis. And you know that the rotation around the x-axis does not change the x value of the vectors, x component of the vectors. A rotation around the y-axis does not change the y component of the vectors, and rotation around the z-axis does not change the z component of the vectors. For example, and you know, using this, you also know how to write down these the matrices, right? These are all 3 by 3 matrices. So the z component should be unaffected. So, so I should write this as 0, 0, 1. Okay, because this is a z component of the vector. The x and the y components get mixed up. So this is some cosine theta minus sine theta, cosine theta, and there should be 0. So just using the fact that the x and the y components have to get mixed up and the z component should be unaffected, I can guess the form of Rz. Similarly, I can guess the form of Ry and Rx also. This is the only 3 matrices possible. Okay, but what about this rotation that is induced in the Hilbert space in quantum mechanics? This seems to be a very complicated beast, right? So let us write down the form of J square. And I will try to make the connection between what is it that we are doing and what is it that this means mathematically. So let us write down J square in the basis. So what is the form? What is the form of J square in the Jm basis? J square is diagonal in the Jm basis. But so let me actually turn this way. I don't know if this will work. So sorry, just give me 1 second. I will. Yeah, so this doesn't seem to work. So I'll just use the landscape orientation. So let me write down the form of J square, right? So in the Jm basis, what are the possible values of Jm? So J equal to 0 corresponds to only one state, which is 0, 0, right? J equal to 1/2 corresponds to two states, plus half and 1/2 minus 1/2. And J equals 1 corresponds to 1, 1, 1, 0, 1 minus, 1 minus 1, and so on and so forth. So if I write down the form of the J square matrix in the basis Jm, what is it that I mean? I mean that I'm calculating J prime, M prime, J square, Jm. Okay, and I know that J square acting on Jm is h bar square J times J plus 1 Jm And I also know that J prime M prime Jm is delta J prime J delta M prime M, right? So if you write down the form of this matrix in the Jm basis, so let me actually write this down. So suppose if I line up the vectors like this, right? 0, 0, 1 half, minus 1 half, 1 half, 1 half, or 1 half. This way, I don't know. 1, 1, 1, 0, 1, minus 1, and so on and so forth. Similarly here, the bra vectors, right? The J square is going to look in this particular fashion. There's going to be the 0, 0, 0, 0 is going to have a value here, right? This is actually going to be 0. Now, the 1 half, 1 half is going to be a 2 by 2 matrix. So let me actually make this a little more. So, okay. The 1 half, 1 half is going to be a 2 by 2 block. The J equal to 1 is going to be a 3 by 3 block. And so on and so forth. And everywhere outside it's going to be 0. Why? Because if you have a matrix element, let us say a matrix element of 0, 0, J square, 3 half, 3 half, right? So this is going to be H bar square, 3 half times 3 half plus 1, 0, 0, 3 half, 3 half, and this is going to be 0. So any matrix element of J square with different values of J is going to be 0. Okay, so this is a very curious form of this whole J square matrix. So this form is actually, it's not a completely diagonal form, because diagonal means there is only one element along the diagonal, but there is still some kind of a diagonal form that is appearing. So there is a block here with a 1 by 1 block, there is a 2 by 2 block, there is a 3 by 3 block, and then there will be a 4 by 4 block, and so on and so forth, and there is zeros outside. So this form of the J square matrix is actually called, it's actually a very important form, it's called a block diagonal form. Okay. Now, if you work out the matrices for J3 or J1 or J2, whatever it is, they're all going to have this block diagonal representation. So J1, J2, J3 all have a block diagonal form. Okay, but the elements inside each blocks are going to be different. For example, in J square case, if you look at the 3 by 3 block, right? So let us look at the 3 by 3. Actually, let me look at the 2 by 2 block. 2 by 2 block of J square. The J square 2 by 2 block is going to be something times 1, 0, 0, 1. Okay, the J3 2 by 2 block is going to be something times 1, 0, 0, minus 1. But the J1 2 by 2 block is going to be something like, it will be have what, 0, 1, 0, 0 or something like that, right? So within this block, how the elements are dispersed within this 2 by 2 block is different. J square and J3 within each block is going to be a diagonal matrix, because these are basically the eigenvectors of J square and J3, and within each block, the J square and J3 should be diagonal matrices, right? Because these are the eigenvectors of J square and J3. But since these are not the eigenvectors of J1 and J2, within each block, J1 and J2 will have off diagonal elements. But J1 and J2 will not have anything outside this structure, which means J1 and J2 also cannot have. So for example, if I write down a similar block diagonal form for J1, I will not have an element, a block over here. That is impossible, because that will marry two different J's, which is not possible because the J's are not, the states are normalized according to this relation. Okay, so whether I talk about J square or J1 or J2 or J3, none of them will have anything that is not of a block diagonal form. But the elements inside each block will be different for J square, J1, J2, and J3, because J square and J3 will have only diagonal elements within each block, but J1 and J2 will only have off diagonal elements within each block. Okay, so this is the first point. The second point is that remember that for every value of J, one can calculate what the corresponding matrix is. So we have calculated this explicitly for the J equal to 1/2 representation. I use the word representation here. I should actually clarify what that means, which I will do. So if I write down the form of U, for example, then the U will also have a similar form. So what is U? The difference between U and the original R is that R is the rotation that happens in the physical space. And because of this rotation, U is the rotation that is induced in the Hilbert space. Okay. The form of this U will also be very similar. It will also have a block diagonal form. It will have a 1/1 block, a 2/2 block, and a 3/3 block, and a 4/4 block, and so on and so forth, as many values as possible. So this will be so there is a specific name for these, a symbol for these matrices. So this is called D1, D with a 1 on top. Excuse me. So this corresponds to J is equal to 0. So D with a 0 on top. This corresponds to J equal to 1/2. This corresponds to J equal to 1, and so on and so forth, right? So the U would also have a matrix form that is also block diagonal in this particular form. So we call these Ds as different representations of rotation. Okay, so I will explain what this means, but I want to stop here and ask if there is any questions about the structure of these matrices before I move on. Any questions or any comments? Okay. So let us now go back to the initial question. The initial question is, look, the R is very simple. I only have 3 matrices, Rx, Ry, and Rz. So if I do the rotation in physical space, I understand the matrices very easily. But if I want to study the corresponding matrices, if I want to study the induced matrices in the Hilbert space, I get an infinite dimensional matrix. Because in this infinite dimensional matrix has a 1/1 block, a 2/2 block, and 3/3 block, and so on and so forth. But this looks extremely complicated. So what is happening? So what is the fundamental thing that is going on? Unfortunately, I cannot explain this in great detail without going into group theory. Okay, and as I told you, I want to avoid a lot of group theory because that will be a course of its own. But I should tell you why things are happening this way. Okay, so when I'm solving the eigenvalue problem of J square and J3, what I'm actually doing is figuring out. So what we have actually done thus far is work out the irreducible representations of the rotation group, which is SO3. Okay. So again, there is lots of words there that probably don't mean much to you. So I will explain what this means in words. Okay. So okay, so let me actually give you an example that I usually give, right? I don't know if I already gave you this example, but so let us say that there is some action that is being performed, right? So let us say that you choose this MSc class and I am giving you an assignment of some sort, right? And I'm asking all of you guys to complete the assignment. Now, one way I can understand what's going on in the classroom is if I look at every one of your assignments separately. But an easier thing to do would be for me to sort of group the assignments. For example, I know that person XYZ work together. Okay. Or let us say persons alpha, beta, and gamma are from the same undergraduate college and they're very good friends. So they always work together. And they gave me the exact same assignment. Or let us say that a group of 5 or 6 students have formed a study group after coming to IIT Gandhinagar. And they always work together. And their assignments are sort of identical to each other, and there might be a couple of changes here and there, But this set of 5 assignments will look very different from, let us say, the alpha, beta, gamma that came from the same undergraduate college, right? So instead of looking at the class as a whole, suppose if I break up this class into little groups and I can understand the action. What is the action? The fundamental action is the working out of the assignment that I have done. So I have inflicted something upon you, right? What I've inflicted upon you is given you an assignment. And I'm trying to understand the response of the class to this action of mine. And I find that instead of looking at the class as a whole, I can understand how my actions impact the class by looking at certain groups of people. Let us say that somebody in the class works alone. He or she does not like to work with other people, and some people are like this, right? So they work by themselves. So this person have to take his or her assignment by itself. But let us say that I know a group of people who work together. Let us say that three people who work together, and I can look at those 3 assignments as one bunch. I can look at 5 different assignments as a separate bunch because these 5 students always work with each other together. Let me say that there is like about 3 BTech students in the class, and the BTech students work with themselves. They don't want to work with the MSc students, so I can look at their assignments themselves. Let us say there is 2 PhD students in the class and they work with themselves. They don't want to work with the BTechs or the MScs, so I can look at those 2 assignments by themselves. So the fundamental problem of trying to understand how my action affects the class, I can now piece it up into how my action affects group A, bunch B, bunch C, bunch D, bunch E, bunch F. And I can understand this whole class as a sum of all these bunches. Okay. Now, what is the characteristic of a bunch? If I look at a bunch of 5 assignments of 5 people working together, and if I look at a bunch of 3 assignments with 3 people working together, I can understand the interconnectedness of these 5 assignments. For example, I can understand that, these people have had the same methodology, same thought process and things like that. And this thought process and methodology is very different from the other group of 3 that work with themselves. Okay, which means I cannot understand the actions of the bunch of 3 people who gave me an assignment. For example, they came from the same undergraduate college, with a bunch of 5 people who are doing PhD in IIT Gandhinagar. These 2 are very different from each other. But they are all trying to do the essential thing. The essential thing is a response to an external stimulus, which in this case is an assignment. So this response to an external stimulus can be understood by piecing up a very complicated object as a classroom into various bite-sized pieces. And the bite-sized pieces have nothing to do with each other. Okay? This is exactly what we are trying to do here. This is exactly what we have done here, honestly. The external stimulus in this case is a rotation in the physical space, XYZ space. But the way this affects the Hilbert space is by piecing up the Hilbert space into various bunches. And these various bunches don't have anything to do with each other. So which means that the rotation that happens in the physical space induces a bunch of representations in the Hilbert space. And these representations are such that there is one object that doesn't care about the rotation at all. So this is the object that corresponds to J is equal to 0. There is 2 objects that sort of mix between each other under rotation. They talk to each other. So if I rotate the state 1/2, 1/2, it becomes 1/2 minus 1/2. There is nothing else to go to. Okay, these 2 states talk to each other, but they don't talk to the J is equal to 0 state. So that's a separate bunch. If I do a rotation and I look at the J is equal to 1 guys, they form a separate bunch. So if I rotate the 1, 1 state, it becomes some linear combination of 1, 1, 1, 0 and 1 minus 1. But it doesn't become 1/2, 1/2 or 1/2 minus 1/2. It is a separate bunch. So the Hilbert space actually breaks up in this very nice fashion. Okay. So this representation, this very complicated representation can be understood as a sum of different representations. So this D that I look at, and again my Bluetooth conked off. Okay. So this D that I wrote here can be understood as a sum of these matrices. So this is D0 plus D1 half plus D1 plus D3 half plus and so on and so forth. But this is not a direct sum of matrices, right? So because if I add two matrices, if I add a matrix A and a matrix B, then the dimension of matrix A and the dimension of matrix B has to be the same, right? Otherwise, it doesn't make sense. I cannot add a 3 by 3 matrix with a 2 by 2 matrix. So when I say that I'm adding these, I'm actually meaning a different kind of add. So to make sure that this is a different kind of add, I put a circle around these pluses. This is called a direct sum. Okay. Another way to actually write this down is the j equal to the d0 representation is simply written as a 0. The d1 half is written as a 1 half. The d1 is written as a 1 plus so on and so forth. Okay, so this notation is also important, which means the action of rotation that happens in the physical space can be understood in the Hilbert space depending as a direct sum of various different representations of this action. So the group here has to do with the fact that the rotation group is an SO3, special orthogonal group. I talked about this in the beginning of the lectures on rotation. The word representation simply means that the action, the stimulus of this external action on the Hilbert space is such that it generates a whole bunch of different ways in which this rotation is realized in the Hilbert space. The way it is realized is a 1 by 1 matrix that has only one eigenvector to talk to, a 2 by 2 matrix that rotates two vectors into each other, a 3 by 3 matrix that rotates three vectors into each other and has nothing to do with the 2 by 2 block, and so on and so forth. So the representation is basically, the English word simply means, how something is represented, right? So the way rotation is represented in the physical Hilbert space of the quantum mechanical system is via these different matrices. Okay. What is irreducible? Irreducible simply means that I cannot reduce the actions of this into simpler blocks. By which I mean, going back to our assignment example, suppose if I have a bunch of 5 PhD students of IIT Gandhinagar working together on my assignment, I cannot understand this 5 in terms of, let us say, 3 of them separately and 2 of them separately. If I can, I will, because the simpler blocks I break it up into, the easier it is for me to understand. But it might so happen that I cannot break them up anymore. Okay, their actions are really intertwined and I cannot break them up into the action of 3 people and the action of 2 people. Okay, in other words, I cannot break this D1 into a 1 by 1 block and a 2 by 2 block. It is actually a 3 by 3 matrix that mixes these 3 vectors into each other. I cannot understand this in terms of anything that is more simple. If I cannot reduce these matrices further, these matrices are said to be irreducible representations. Okay, the irreducible simply means that the matrices cannot be broken up further. Representation means that this is one way in which this rotation is realized in the Hilbert space of the quantum mechanical system, and the group here has to do with SO3. So this is actually called a direct sum of matrices. And in the next class, I will talk about this mathematically. I will explain what this direct sum actually means. How do you construct the direct sum of two matrices? And then we will construct one other way in which I can construct a linear vector space, and that is called a direct product or a tensor product space. Okay, so I will talk about direct product and tensor product in the next class. I will develop what this means using some very simple examples, and then we will move on to the subject of addition of angular momenta. Okay, so for today we'll stop here, and I can take any questions if you have.